Hello, and welcome to a video series on MAC 2311 Calculus 1. My name is Sean Perry. These are guided notes number 1 in the series, An Introduction to Limits. One of the fundamental ideas in calculus is change. Specifically, we want to know how one numerical quantity changes when some other related quantity changes in a particular way. Specifically, we're going to want to see if when one quantity gets closer to another, some other related quantity is going to get closer and closer to a certain value. To start to describe this, let's take a look at this collection of symbols called a limit. We would pronounce this collection of symbols as the limit of f of x as x approaches c is equal to L. Let's break this collection down into pieces. Here I've color-coded some of those pieces. The expression LIM is basically our denotation of a limit. We pronounce this the limit of. We're going to look at its argument, given here as f of x, and see what its behavior is. What are its numerical values? As a certain other value, let's say its input x, approaches c. That's the meaning of this arrow here. X should be imagined as getting closer and closer to some value c, and we want to know what f of x does. If f of x settles down and becomes closer and closer to a value, here given as L, this is just a number, then we would say that the limit of f of x as x approaches c is L. Now we're going to talk a lot more about limits and do a bunch of examples, but first let's go into some more detail about the components of this expression. First of all, we have perhaps the most mysterious and important of all the symbols, which is this little arrow right here. This symbol is doing some serious heavy lifting for us, and we're going to want to furnish some intuition about what it really means. A little bit of a hint is from the verbiage we use to describe that symbol. We say that x approaches or tends to, or sometimes just x goes to c, where c is some constant. That is to say, in your problems, c will just be a number. To be very particular about my vocabulary here, c is not a constant the same way that pi or e or 47 is. It's a parameter. It's going to be a letter which takes on a single value at the beginning of a problem, but then it's just going to maintain that value for the whole problem. On the other hand, x is a true variable. That is to say, it can take on many values. And what you should imagine is that this variable is taking on values which get closer and closer to c, and they don't wander away from it either. They go towards c, and they stay close to c. Now, what your imagination does with those values is kind of up to you. You could imagine a continuous trajectory, x's traveling towards c in a line or a curve. You could imagine it sequentially. You could pick some values for x and imagine that they become closer and closer to c as you count up discretely. And while we're just imagining things, this could be a complicated trajectory or a simple one. You can imagine it bounces around C, getting closer and closer from above and below. You could imagine it just jumps to C immediately, and there it stays. Actually, this last one here is a bit of a joke. That is to say, yeah, sure, if the x's were all equal to 1, we would say that this sequence approaches 1 or converges to 1, but when we're going to talk about limits, which is the main focus here, we're usually going to want to not consider when x is equal to c. The reasons for that are going to be clarified where we see some of the main applications of the limit. Now, even though, as your imagination will tell you, there's many ways that x could approach c, we are going to consider two main approaches. Either x coming from above c and descending down towards c. This is sometimes called a right limit, or approaching c positively. And what we mean is we start with values bigger than c, and then we go down ever closer to c without going past it. The opposite of that would be approaching c from the left, or approaching c negatively, sometimes called a left limit. And what that means is that we're starting from values less than c, and we're increasing ever towards c, getting closer and closer. This sequence and this trajectory that I picked here, these are examples of a left limit. We're starting underneath or below the value of c, and we're getting closer and closer from below. If we looked at that on a left-right number line instead, that would be from the left. Let's think about some sequences or trajectories of x which approach certain values. For example, consider 1 over n as n gets larger. That is to say, as n goes towards infinity. X, following this path of values, that is to say, here we have it at 1, and then it gets lower until it gets to a half, and then a third, and a fourth, and a fifth, and so on. These are getting smaller and smaller, but they're approaching the value 0. And we would write this kind of thing as x approaches 0 positively. Here is that collection of symbols here. Likewise, here's a specific approach for x approaching 0 negatively. Let's consider a negative 10 to the negative n. And let's actually just take n to be a natural number here. I'll write that this way. N is a natural number. If you're not familiar with pitchfork set notation, that just means that this little n is an element of the set of natural numbers n. And I'll take the set of natural numbers to be 0, 1, 2, 3, 4, and so on. Now, if x were to follow this trajectory towards 0, if it was to approach 0 in this way, we would say it was approaching 0 negatively. I chose these to be negative values, so they are less than 0. And they're getting bigger, actually, because these are smaller and smaller negative quantities, that is to say, of smaller magnitude. And so you can kind of see from this quick plot that I've done that we are getting closer and closer to 0, but we're doing it from below. We are doing it from values less than 0, and this is what we mean by we are approaching 0 negatively. Now, as far as the function notation f of x is concerned, I'm going to presume that's known to the watcher of this video. If you're hazy on that topic, I have a couple of algebra series on YouTube. Please consult these series if you want a refresher on that topic. Suffice it to say, f of x, like c and perhaps L, these are going to be given in the problems that you're looking at. There'll be some specific f of x we have in mind. And the idea of a limit is to ask if this output value, f of x, this dependent variable, does it itself approach some value as x approaches c? What does it do as x approaches c? We want to examine its numerical behavior. So let's ask a couple baby questions. What is the right limit and the left limit of x squared as x approaches 0 positively and x approaching 0 negatively? For a right limit, or a positive approach, let's consider some descending powers of 10. We have x is equal to 1, x is equal to a tenth, x is equal to a hundredth, a thousandth, and so on. And we take a look at the x squared values and see that these are 1, a hundredth, a 10,000, and a millionth. And we can see that x squared is also approaching 0. And so we would say that the limit of x squared as x approaches 0 positively is 0. Likewise, for x approaching 0 negatively, let's take a look at the dyadic fractions. That is to say, they're negatives. Let's take a look at negative 1, negative a half, negative a quarter, negative an eighth, which is going towards 0 from below. And we can see x squared is 1, a quarter, a 16th, a 64th, and so on. And we can see these are also descending down to 0. So x squared also approaches 0 as x approaches 0 negatively. I think it might also be nice at this point to examine this graphically. Here I have a graph of x squared. And let's imagine that we were taking on x values, starting from above 0, and looking at the y values and seeing what they themselves did. So for example, if I started with these x values and got closer and closer to 0 from the right, then my y values following this curve, the y values would be getting ever closer to 0 as x got closer to 0. And likewise, if we came from this side, there wouldn't be much of a difference. We'd be going along this curve, heading towards 0, just as x does. Now, you might have noticed that the first collection of symbols we used for the limit didn't have a plus or a minus in it. In order to say that the limit of f of x as x approaches c is equal to L, we need to make sure that both the approach from the right and the approach from the left give me the same thing. We only say that this limit is equal to L if the right and left limits are also equal to L. This is an if and only if condition. If the limit of f of x is L as x approaches c, then the left and right limits must match. But usually we're thinking about things in the reverse direction. That is to say, when we want to check and see what a limit is, we check its right limit, is it L? We check its left limit, is it L? And then we know that f of x has the limit of L as x approaches c. Now, there's an interesting fact that if a positive approach gives us a certain limit L, then that's going to work for any positive approach, and similar for the left limits. We're not going to prove that here in this class, but I invite you to contemplate why it might be true. And it's a very nice fact, because that means when we want to check a limit, we really only have to check one positive approach and one negative approach. In a similar hand-waving fashion, I'm not going to prove that all we have to check are left and right limits. I'm just going to take that as the definition for a limit in this case. But you should know the rabbit hole gets very deep, and eventually we might have to consider how we approach a certain value of c and make sure that any approach is going to give us the same limit L. But that's a story for another time. Let's do a more concrete example where we see a limit which does not exist. Consider this stepwise function here. F of x is defined to be x plus 1 when x is less than 0. It's defined to be x minus 1 when x is greater than 0. And it's defined to be 0 when x is equal to 0. Now, if I approach from above, we're following this curve, and we see that as x gets closer and closer and closer to 0, these y values are getting closer and closer and closer to negative 1. And likewise, if we come from below, then these y values are getting closer and closer to positive 1. There's a certain gap here. This gap, this jump between this left limit and this right limit, these are going to be called jump discontinuities. And they cause the left and right limits to be different. If the left and right limits are different, then the total limit, what is the limit as x approaches 0 of f of x here, it does not exist, right? It gives us two values rather than one, and we need a single answer here. So when we see this kind of jump discontinuity, we know that the full limit will not exist. And so in these cases, DNE or does not exist or there is no limit, these are all appropriate responses when someone says, what is the limit here as x approaches 0? So we can see that even though left and right limits can exist, if they're not equal to each other, then the total limit, which I'll just call the limit, does not exist. Now, here's one of the reasons that we don't necessarily want to consider values equal to c, trajectories where x is equal to c, when we are considering limits. And that's because the function not being defined at the point in question doesn't really obstruct the limit as long as all of the rest of the points are defined. So let's take one of my favorite functions that has a hole in it. F of x is equal to x over x. So you might think this is just 1, and it certainly is everywhere except for 0, but 0 over 0 is an undefined quantity. And so this graph doesn't really have a value at this point, 0, 1. But because all of the other points, the y value is equal to 1, f of x is equal to 1, as we approach from the right, we're just getting 1, 1, 1, 1, 1, 1, 1, so we can see that's sort of converging to 1. And when we approach from the left, we still have a bunch of 1s here. And so from the perspective of the line, without looking at where we're going, without looking at the fact that there's this big old hole coming up in the graph, it really just looks like we're marching along, just ticking off 1s as our y value. So we would say in this case that the right limit and the left limit are 1. And if the left and right limits are equal, well, hey, that means that the total limit is also equal to 1. So even though this function lacks a value at this point, even though there's a hole in the graph, we would still say that the limit of this function as x approaches 0 is equal to 1. Now, this kind of discontinuity is called a point discontinuity, to contrast that with the jump discontinuity we just saw. And we'll talk more about the idea of continuity in a later video. But for now, you should know that a point discontinuity doesn't really usually cause the limit to fail, not without something else going on. A point discontinuity, well, from the perspective of the limit, it still looks like we're headed towards the same value for f of x, so the limit still exists, even if the function value does not exist. Now, let's think of another way that a limit might fail to exist, because you might be thinking that maybe left and right limits just always exist. Well, here's one of my favorite pathological functions. This thing is not very well behaved. We take 1 over x and we compose that into sine. And if we wanted there to be a defined value at 0 to take care of this not being defined at 0, we could define it to be 0, that's fine. But really we're focused on what is the approach here? What's happening when we are looking at values away from 0? What does this function do? And the idea is that as you plug in small positive numbers here, going towards 0 with x, this 1 over x is going through larger and larger values. It's actually running through the entire real number line as x is getting closer to 0. And that causes sine to oscillate through every oscillation that it would across the whole number line. So there's an infinite number of oscillations going on in this little bunched up region here. And the idea is this causes both the left and right limits, and therefore the total limit, to not exist. Because when we say something approaches something else, remember, we need it to get close to a value and stay close to a value. And even though this function is kind of trapped between -1 and +1, it never settles down and approaches any one given value. It just jumps and wiggles back and forth, faster and faster as you approach 0. And because there's no settling down, f of x doesn't really approach or stay close to anything as x approaches 0. There's just too much wiggling. And so in this way, the left and right limits fail to exist, and so the total limit would also fail to exist. And that's most of the facts I want to tell you about the limit. There's just a couple more. One is that we could, notationally speaking, really just rely on our arrow symbol for convergence in order to write the limit. Let's recall that this double arrow here means if-then. It's a conditional arrow. So this would be if statement A is true, then statement B must also be true. And using that, we could actually write the limit of f of x as x approaches c is equal to L in the following way. If x approaches c, then f of x approaches L. And so this other arrow notation here is also a completely valid representation of the limit. It's just not as compact or common as this notation here. But it is a good idea to keep in mind that we are talking about two convergences. We're saying when x goes towards c, then f of x goes to L. And so maybe this is a good kind of notation for ingesting what's really going on with the limit. One other item I want to briefly touch on to close this introduction is that we haven't really been rigorous. We've used a lot of hand-waving words. I've used expressions that are very physical, like x goes to c, or x approaches c, or f of x tends to L. You know, these aren't rigorous definitions of things. And I've given you some examples, but an example is not a proof. It's not a definition. So how would one go about really firming this up and making this an unambiguous mathematical expression? We want to do better than just say that x gets close to c and stays close to c. What does that mean? What could we do to sort of firm that up? And one of the first things we want to address is that when we say close, we don't just mean kind of close. We mean arbitrarily close. That is to say, as close as you could possibly want. It means that there's no obstruction to getting even closer as long as we're not on top of the value itself. So here's the game. Let's pick a small value, any small value you like. We'll call it delta. That's the squiggly symbol here. It's a Greek D. Let's let it be a tiny number, like a millionth of a unit, or a trillionth, or 1 over 2 to the 10 to the 10. You know, something ridiculously small. Well, eventually, we want the magnitude of x minus c, or the distance from x to c, to be less than that. That's what we mean by arbitrarily close. Smaller, eventually, than any positive constant. Now, keep in mind, since we're not going to be considering x equal to c, we also have that this distance is bigger than 0. So eventually, we will have something which is smaller than delta, but greater than 0 as far as the distance from x to c is concerned. So we formally express that with this inequality. If you gave me a tiny number delta, eventually x minus c would be greater than 0, but smaller than that. This is what we mean by arbitrarily close to c. Now, we're also going to have to keep track of the second approach, that is to say, as f of x approaches L. So we're going to use a tiny number here, which we'll call epsilon. That's this little other Greek letter right here. And it's also some arbitrarily small number. Then we can use our arrow definitions of the limit to really give a good, firm definition, an unambiguous definition about what limits mean. Here is it in its pieces. You tell me a small number epsilon, that is to say, how close do you want f of x to have to be to L? Then I'll tell you a small number delta, that is to say, get x that close to c. And if we know that x is that close to c, it must be the case that f of x is that close to L. That is to say, if x is closer than delta to c, f of x is forced to be closer than epsilon to L. Now, if you're the kind of person that's just in love with squiggles, you could write this in one fell swoop with the universal quantifiers for all and there exists, which looks like this. This is sometimes called the analytic definition of the limit, and it says that for every epsilon greater than 0, that is to say, for any tiny number bigger than 0 you could conceive of, then there exists a tiny number greater than 0, such that if x is that close to c, then f of x is that close to L. Then to just say it all at once, we have, for every epsilon greater than 0, there exists a delta greater than 0, such that if the magnitude of x minus c is between 0 and delta, then the magnitude of f of x minus L is less than epsilon. Now, I think this would make a really sick armband tattoo, but other than that, we're really not going to be using this definition too much at this time. Later, we're going to work more closely with this definition. I'll show you how to execute a proof like this, but for right now, I wanted to actually help you furnish some kind of additional intuition and just let you know that at the end, your intuition is going to be grounded in a rigorous mathematical expression. It's not just to bamboozle you, although I do think it looks pretty cool. The final thing, actually, that I'd like to make sure that we're all on the same page about is what do we think about expressions such as x approaches infinity, or 1 over x approaches negative infinity. So these uses of infinity might not really jive with what we've said already about approaching arrows. And that's because x never really gets close to infinity. It gets bigger and bigger, but what would it mean to get close to infinity? For any number, right, it's still infinitely far away from infinity. So we can't really talk about its magnitude in the same way that we could if we had put a number in here for infinity. We'll just get infinity back. So we have to mean something a little bit different when we talk about limits approaching infinity. Really, all you should think about when we talk about x approaching infinity is that x just gets arbitrarily large. It gets bigger and bigger, bigger still, and it never really has to stop. If you pick any fixed value, x will eventually be larger than that. That's what we mean by arbitrarily large. And you should maybe contrast that in your mind with what we meant by x becoming arbitrarily small. Like if x approaches 0, then for any fixed value, it'll eventually be smaller than that. And also, I suppose, larger than any fixed negative value as x approaches 0. So that's what we mean by having arbitrarily small magnitude. And that sort of is a foil to x approaching infinity, where it has eventually arbitrarily large magnitude. Likewise, we should know how to make sense of an infinity that shows up as the L value. So consider, for example, 1 over x, my favorite hyperbola. If we consider the left limit here, then as x approaches 0, we are going along this curve and then dropping off, hugging the vertical asymptote. And we go off down towards negative infinity, getting negative values of larger and larger magnitude. So as x gets closer and closer to 0, this decreases without bound. And that means that we would say the limit as x approaches 0 negatively of 1 over x is equal to negative infinity. And likewise, I suppose, if we approached from this side, we'd shoot off towards positive infinity. What would that mean about the total limit? So we will cover these ideas and more in the practice for this chapter. But that's going to do it for this video. Thank you very much for your patience. Good luck with your studies and have a great day. I'll see you in the next one.